So today we'll be talking about model-based reinforcement learning and how it can be used for multitask learning. So for today, first we're going to recap goal-conditioned reinforcement learning and relabeling. Then we'll talk about model-based reinforcement learning and how it can be used for multitask learning. And then we'll talk about model-based RL when you have higher dimensional observations, such as images. And the goals for today will be to allow you to understand how to use and implement model-based reinforcement learning methods, how to use, how model-based reinforcement learning can be used for multitask learning, and challenges and strategies for model-based RL when you have high-dimensional observation spaces. Great, so let's start with the recap. Last Monday, before the project presentations, or before the proposal presentations, we talked about first briefly overviewing reinforcement learning, and in particular, Karol introduced model-free reinforcement learning methods, including policy gradients and Q-learning. Karol talked about how reinforcement learning algorithms in general follow this structure, where you first generate samples by running the policy, fit some model to estimate the return that those samples get, and then use that model to improve your policy. We saw two different ways for doing this. The first was using policy gradients, which fits kind of a model to estimate the return by simply looking at Monte Carlo rollouts of your policy and computing the discounted return from that rollout. And the second approach is to use Q-learning, where you fit a Q function using the Bellman equation to estimate your return. Both of these are two ways that you can use to estimate your return, one where you just average over the trajectories, and one where you actually fit something like a neural network. And then once you have this model of the return, you can either use it to directly update your policy using a policy gradient, or use basically your Q function, take the maximum over actions to get the best action for your policy. Okay, and then, so these are kind of two model-free reinforcement learning methods. And then later in this lecture, once we get into the core of the lecture, we'll focus on model-based reinforcement learning methods. We also talked about what is a reinforcement learning task. We talked about how basically a task corresponds to a Markov decision process with a state space, an action space, an initial state distribution, transition dynamics, and a reward, where all of these might vary across different tasks. And you can alternatively view a multitask reinforcement learning problem as something that tries to integrate a task identifier into your representation of the state, where this S bar is the original state. So this just puts the multitask, the set of MDPs into a single MDP, where you can then condition your policy and condition your Q function on the task identifier in order to get a multitask policy or a multitask Q function. What does ZI correspond to? This can correspond to a range of things. It can correspond to a one-hot task identifier, which is the simplest case. It can correspond to a language description of the task. This would correspond to an instruction following setting. And it can also correspond to a desired goal state. So you could have a multitask RL problem where different tasks correspond to trying to reach different states, different goal states. And this is a special case of multitask reinforcement learning that's called goal conditioned RL, in the sense that you are going to be conditioning your policy and your Q function on the goal that you want to reach. And you're going to be training this policy and this Q function to reach goals. Okay, with this, we can look at an example of a multitask RL problem. So this is the example that Karol gave last week, where you have a hockey player. Maybe there's the hockey player has a teammate, as well as someone on the other team that's defending the goal. And you have two tasks. One task is to pass it to the teammate, and another task is to shoot goals. And in this example, if you think about the case of a setting where maybe you were trying to shoot a goal, but you accidentally performed a great pass to your teammate, in this case, it makes sense to actually share that data and not just use that data for the task of shooting the goal, but also use that data for training your passing policy. So to do this, you can store your experience as normal, but also relabel your experience and relabel it with kind of the ID of this, of the ID of task 1, for example, if you're originally trying to do task 2, so this actually should be task 1. Say that, okay, in retrospect, let's say that I was pretending to perform task 1, I was pretending to pass, I did a great job at passing. You can store that experience with the corresponding task ID and the reward, and allow yourself to learn with that data for both this new task as well as the original task that you were attempting. And this is what's called hindsight relabeling. It's also referred to hindsight as experience replay, or HER. And the way this works as an algorithm is you collect data that has the original states, the actions, the goal state that you're attempting, and the rewards using some policy. You then store that data in your replay buffer. And then when you want to perform hindsight relabeling, you relabel your experience in DK using the last state that you reached as the goal. So instead of storing it with the goal state that you're attempting, you can replace that goal state with the state that you reached in practice. And this gives you an example of a success for that state. And then you also set the reward to be something like the negative distance between the current state and that new goal state. Once you store this relabeled data in your replay buffer, you can then update your policy using all of the data that you have, including the relabeled data. And then you can iteratively apply this process. There may be other relabeling strategies as well. So in this case, we relabeled with the final state that we reached as the goal, but you can also use any state from the trajectory. This will allow you to alleviate exploration challenges by trying to target the way that you share data across tasks. Okay, is there any questions on this process?
Hello?
Yeah, go ahead.
So from this slide, it seems that the final state as of big T is like your target state, but how can you make sure that's the case?
Yeah, so basically when you collected the data, your goal state was randomly sampled, for example, and stored in your data. And this is saying, in retrospect, let's say that my goal was actually the state that I reached, and store the data with that kind of state that I reached as the goal.
Okay, I see. Okay, thanks.
Any other questions? So this is the algorithm that you'll be implementing in homework 3.
I have one question.
Yeah, go ahead.
The last state that is reached is like not a good state for the task. Let's say in the case of example of the hockey player, the bot scores an own goal. So like that's not a good state to be in. So, but we do not want to reward, train on that particular kind of strategy, because that would be like unreasonable. So how to prevent that?
So if that's a goal that you don't want to reach, note that in this case, we're still passing in the goal to our policy. So we're training our policy with like a given S and SG. And so essentially what this is going to be doing is it's going to be training it such that if you wanted to score a goal on yourself, for example, with that particular goal state, then that's the way that you should, that's kind of an example of how you could do that. This won't necessarily harm the other policies. It won't tell the other policies for other goals to score a goal on yourself. It's only going to be rewarding the policy with that goal that's like actually a good thing to do with that goal state. That's a good thing to do. So basically, if ST is is scoring a goal on yourself, then you'll set that to be the goal state here, and you'll give it a high reward for doing that, but of course, only for this policy.
Okay, thank you.
Do you have a question?
Sorry, I was muted. Yeah, I'm assuming here that we want to be selective in terms of what we add to the replay buffer. So is this strictly driven by the reward? Like at the end of the episode, we look at the reward and then we think that, oh yeah, this is a good result, and that's what I will add to the replay buffer.
Yeah, so the intuition here is that if you choose the last state or one of the states in the trajectory, that's an example of something that you achieved on accident, and you can use that kind of accidental success as like data as if you did want to accomplish that. If those kinds of goals are things that you don't care about, like scoring a goal on yourself, for example, you could choose to only relabel within the set of goals that you care about, for example. There's also kind of a generalization of this where you could, instead of in the setting where you're goal conditioned, if you're in a multitask setting, you could see if the experience you collected had a high reward for any of the tasks and relabel for tasks that it has high rewards for. And this is kind of a heuristic that allows you to store data that is successful for different tasks that you weren't trying to accomplish. You could also store data in other ways. This isn't the only way to relabel your data. This is just one heuristic that tends to work well because it stores basically successes of these other tasks. Does that answer your question?
Yeah, that does. Thanks.
Yeah, and then it's asking, so basically this allows us to gain a lot of data for potential successes, right? And that's exactly right. It's asking, so are we adding more tasks by adding different goal states? And that's also kind of generally correct. Basically, each goal state corresponds to a different task, and each time you kind of experience reaching a new goal state that you hadn't seen in your data before, that may actually correspond to adding a new task. Is asking, does relabeling significantly slow down the training process? It will increase your replay buffer size, but it won't necessarily slow down the process of learning in comparison to goal conditioned learning. And actually, typically it makes learning actually faster and more efficient because it actually helps alleviate exploration challenges by storing data of successes. And then is asking, shouldn't we constrain that if ST is one of the goal states for one of the tasks that we want to perform, and then only perform this augmentation? Yeah, so if you have a set of tasks that are the ones that you care most about, then you could choose to relabel only for those sets of tasks. So basically have a rule here that says like, if ST is like in my set of goal states, one of the reasons that we may not want to do this, I think this could be a very reasonable way to approach things. And one reason that where it may make sense to actually relabel with any possible state is that it may actually help the model learn about general ways to reach states. And that kind of general learning process about how to reach different states may be useful for the weights of the model to learn how to accomplish different kinds of goals. Okay, great. And then also going back to the question about it slowing down training, you'll also get an opportunity to experiment with this in your homework. So you'll be able to understand exactly what the ramifications are. Okay, and then how does this actually work in practice? So the 2017 paper that introduced this concept, that was actually also somewhat introduced in this 1993 paper by Leslie Cabling. The 2017 paper experimented with the simulated robotic manipulation task, where tasks corresponded to pushing, sliding, and pick and place of objects on a table. And what they find is that when you use relabeling which is in the blue and the red curve here, they have two different versions of it. They find that you're able to get pretty substantial benefits over either count-based exploration or just a vanilla version of the algorithm, which is kind of evidence for how well or how this can alleviate challenges with exploration. Okay, great. So that's a brief recap of what was covered on Monday last week with regard to reinforcement learning and goal conditioned reinforcement learning. Now we'll get to the kind of core part of this lecture on model-based reinforcement learning and how it can be used for multitask learning. So the main idea behind model-based reinforcement learning is that you're going to learn a model of the environment dynamics. And the reason why you might do this is that it often leads to better data efficiency, because if you learn a model of the environment, you can then actually leverage that model when figuring out what to do, rather than collecting data from the real environment. And this allows the model to be easily reused. And as we'll talk about in a couple slides, the model can actually be reused across different tasks in many different contexts. The way that it looks like in the context of this loop that we talked about before is when we're fitting a model, we are estimating the transition dynamics using some neural network. In the slides, I'll denote this as a deterministic neural network that predicts S prime from S and A. But in practice, this network may actually be stochastic in order to capture stochasticity in the real world. And this just kind of comes down to a supervised learning problem, where you want to minimize the error between your predicted next state and the true next state. Then once you learn this model, you can then optimize for behavior or for a policy using that model. And we'll talk about exactly how that happens in a couple slides. But kind of at a high level, we're going to be fitting a model of the environment and the dynamics, and then using that model to improve the policy. Okay, so what does this have to do with multitask reinforcement learning? Before we talked about multitask reinforcement learning as having potentially different dynamics, different reward functions, different states, and different action spaces. And one observation here is that in many situations, the only thing that varies across tasks is just the reward function. And in particular, today, we're going to focus exactly on this special case where the state space, the action space, the initial state distribution, and the dynamics are the same across all of the tasks. And only the reward function varies with the task. And a few examples of where this may come up. One example is robotics, where the laws of physics are staying constant across tasks, but you want the robot to complete different objectives. So maybe you want to do laundry, maybe you want to be able to cook for you, and so forth. In this case, maybe the dynamics will often be the same, and the only thing that's different is the reward function that you're giving it for doing these different tasks. Another example is in a task-driven dialogue system, where maybe the user that the dialogue system is interacting with is constant, and the language is also the same, but the user has different objectives that it wants this dialogue agent to be able to complete in different scenarios. Maybe in one scenario, the user wants the dialogue agent to order food. In another scenario, it wants it to provide emotional support, and so forth. And then one third example where this special case also holds is in autonomous driving. For example, maybe the rules of the road stay constant over time. You're always in the same country or in the same kind of region of the world, but what might be varying is different user preferences. So different tasks would correspond to driving for different people, and one person may want the car to go very fast, another person may want the car to drive very smoothly. Okay, so this is the special case that we'll focus on today. And in future lectures, we will also be considering scenarios where things like the dynamics may be changing over time. Now, one of the things that's nice about the special case is that now estimating the model is just a single task problem. You just need to learn a single model of the world, because that's constant and only the reward is changing. So that means that we can kind of readily apply several standard model-based single task learning methods for these multitask reinforcement learning cases. Okay, so how do model-based RL algorithms work and how do they optimize these objectives? So the first approach that we'll consider is optimizing over the actions using the model. There's a few different ways that we could do this. This is also referred to as planning, in the sense that you're planning a course of action using the model and the task that you want to complete. The first way that you could imagine doing this to optimize over these actions is just with backpropagation. So you could take your reward function and backpropagate gradients through your model into your sequence of actions and optimize over a sequence of actions with gradient descent that lead to a high sum of rewards. So this could be with a gradient-based optimization. And the way that this algorithm works is you first run some policy to collect data. You then learn a model to minimize your model error. And then you backpropagate through that model to choose a sequence of actions, A1 through AT, for example. And then you execute those actions. And you can backpropagate to just choose those actions directly and execute those actions directly, or you could pass those gradients into a policy and optimize over the parameters of this policy. Any questions on how this works at a high level?
Just a question about steps 2 and 3. So we're using the same trajectories to minimize like the model of the environment as well as the policy.
Yeah, this is a good question. So we will, I guess, so in this case, this is going to be using your data. In this step, it depends on how you optimize, but you don't actually necessarily need data for this step. So for example, say the case that you're just optimizing over a sequence of actions, A1 through T. What you can do is you can just randomly initialize these actions and then pass them through the model and kind of iteratively, maybe this is kind of the first iteration, iteratively update and optimize this sequence of actions such that it maximizes the reward or the sum of rewards. And to do this optimization, you don't actually need to optimize it over data because you're optimizing over the action sequences, and you can actually generate kind of fake data from the model itself.
Okay.
Asking, does it require a continuous action space for backpropagation to work? The short answer is yes, although there are also gradient estimators that can approximate gradients through discrete things. This includes things like the straight through estimator, Gumball softmax, etc. Do you have a question?
Yes, so I just want to clarify that in step 3, we do not run simulations and interact with the environment. We only use this learned F to choose actions.
Correct, yeah. So step 3 isn't involving the environment in any way. You're just kind of involving your learned model, which can be viewed as a learned model of the environment, which you're using to optimize it for your actions.
Thank you.
Okay. Then another approach that we could use instead of a gradient-based optimization over actions is to use sampling, which will essentially just correspond to a gradient-free optimization and can actually work surprisingly well in some cases. And the intuition for why a gradient-free optimization might make sense is that the sequence of actions may be fairly low dimensional, certainly lower dimensional than the size of a neural network parameter vector. And the way that this works is the first two steps are the same. You collect some data, you train a model, and the third step is a little bit different. So instead of doing a gradient-based optimization, you instead iteratively sample a large number of action sequences, run those action sequences through the model, and either pick the action sequence that led to the highest reward, or pick the top K% of action sequences, and then kind of iteratively refine that set of action sequences. Where, for example, you can pick the top K%, fit a new distribution to that top K%, resample from that distribution, and allow yourself to iteratively get a better and better sequence of actions. So there's a variety of gradient-free optimization approaches that you can use. One is what's called random shooting, which is simply where you just randomly sample a bunch of action sequences and kind of shoot them out, which is why it's called shooting, and then pick the one that works the best. Another is called the cross-entropy method, which may sound a little bit confusing. It doesn't really have much to do with the cross-entropy loss, which is the iterative approach that I mentioned before. And there's also things like evolutionary methods, which are other forms of gradient-free optimizations. One thing that is nice about this is it's pretty easy to apply these methods to discrete action spaces, although it also actually works pretty well for short horizon continuous action spaces. Okay. So now this is kind of V1. How can this approach fail? Does anyone have thoughts on what might go wrong with this approach? Feel free to either raise your hand or answer in chat. Any guesses? Yeah, so there's one comment from which is that there's no exploration, so the model might always choose from a small set of actions that may not be very good. Mentions that it ignores future rewards after the horizon. So yeah, each of these approaches were only optimizing for a fixed horizon of kind of a fixed horizon from like 1 to t, for example. And if you have a very long horizon problem, this may not work well. Mentioning that if the model is inaccurate, you're going to have compounding errors because you need to predict multiple time steps into the future. And if you get a small error from the model and it starts to kind of fall off the manifold of what it's seen before, then it's going to make bigger and bigger errors and be actually quite inaccurate as you have longer horizons. Is hypothesizing that maybe there are problems with inaccuracies in the data. Cool. So all of these are good answers. The main thing that I actually have on the slides is point, which is that the action optimization, if you have an inaccurate model, especially when you have compounding errors over time, this optimization over actions will exploit any imprecisions in the model. So if the model is erroneously optimistic about one set of action sequences leading to high reward, then it's going to try to actually find the actions in which the model is inaccurate because the model is telling you that leads to high reward. Now, one really easy way to fix this to some degree is to refit the model using new data. So this will specifically happen when the model specifically will be imprecise when it's off of the manifold of data that it's seen before during training. And what we can do is we can then collect new data from the action sequences that we optimized, which will precisely be in the situations where our model may be inaccurate, and use that data to retrain our model to be accurate in those regions. So we can basically just add a fourth step to this algorithm where we actually execute the planned actions and then append the visiting data to our data set, and then retrain our model using all of the data that we've seen so far. Okay, so this is kind of the full version 1 of the algorithm. Even in this case, it can be, retraining the model using new data will definitely help with these sorts of imprecisions. But in the general case, learning a good global model is pretty difficult. There are a few different ways for tackling this problem. One additional way that we can use to tackle this problem is whenever we find ourselves in a new state, you can, instead of just kind of keep on executing the plan that you had derived before, actually replan using your model at that new state. And this can allow you to potentially kind of correct for errors that you made at that previous time step. And this is what's called model predictive control, or MPC, which is a bit of a fancy name, but the gist of what it means is to plan and then replan using your model. So the way this looks like is you first run some initial policy to collect data, learn a model using that data, use your model to optimize over an action sequence. All of these first 3 steps are the same as before. Now what we're going to do is we're going to execute the first planned action. So in this case, maybe we're at time step T. We optimized for an action sequence from AT to AT plus H. And here we're going to execute only AT, observe the next state, append this to our data, and then we're actually going to kind of replan at the next time step. Now we'll be at kind of replanning AT plus 1 through AT plus 1 plus H. I'll write it down here. And then again, executing the first planned action. And of course, you can also still have this outer loop that retrains your model as you see more and more data. And essentially what this allows you to do is you start making a wrong turn and see yourself in a state that you didn't expect to be in, then you can correct yourself at the next time step. And this can actually help a lot with model errors, including compounding errors. The downside is that it's actually pretty compute intensive because you need to run the planning process much more frequently than just at the very beginning of the trajectory. So this is one approach that can help with model errors. There's a number of other approaches as well that we won't have time to get into. This includes things like uncertainty estimation, where you try to measure the uncertainty of your model and be conservative with regard to your model's uncertainty. There's also approaches that try to use only a local model and constrain the action optimization to be close to where the model is accurate. Okay, so that's the gist of how model-based reinforcement learning algorithms work. What does this have to do with multitask reinforcement learning? How you actually apply this to a multitask RL problem depends on the form of your reward function. So if you know what the reward function is, if you know how to evaluate it, then you can just learn a single model of the dynamics. And then when you run the planning procedure to optimize over your actions, just whenever you do that planning process, you consider the reward function that you care about at test time and plan with respect to that reward function. So for example, this is actually a recent paper from a year ago where reward functions correspond to different pencil trajectories, and it's basically able to replan with a single model to write different digits. So here is like a digit, I think a 5, I think there's a 4 here, a 7 here, and so forth. So it can use its model and plan with regard to these different tasks of writing different digits. Another example is the different tasks may correspond to trying to manipulate balls in the palm of a hand. I think they're called bounding balls in this case. And for example, this first task may be to rotate them counterclockwise. A second task might be to simply just put this ball in a certain position as indicated by the red dot. It's a little bit hard to see. And then a third task might be to rotate the bounding balls clockwise, which the model is also able to figure out how to do. And one of the pretty cool things about this, actually, before I go into that, one caveat here is that the reward function will actually change how you collect the data. So if you have that outer loop that's actually collecting, that's telling you to collect data, it's basically collecting data based on the actions that you select, then you'll want to be collecting data for these different reward functions rather than just collecting data for a single reward function and then trying to generalize to a new reward function. One last note is that these algorithms are actually quite sample efficient, and they're actually efficient enough to be able to train for this task on a real robot. I think that it took on the order of a couple hours to learn how to manipulate these bounding balls in the real world. Okay, so that's the case where we know the reward function. In this case, the reward function was just, for example, the position between the goal position, the negative distance between the goal position of each of the balls and the true position of the balls, or the distance between the trajectory that was drawn and the goal trajectory. But in other cases, you don't necessarily know exactly what the form of the reward function is for each of the tasks. And so you might need to actually learn a model of the reward function, which you can just learn with multitask reinforcement learning, or sorry, with multitask, it's just standard multitask learning. Or you could also use meta learning to meta learn a reward function with a little bit of data, with a few examples of what that task is. And then once you get this kind of parametric form of the reward, you can use that to plan. So as an example of what this looks like, say you want the robot to put this pencil case above or behind the notebook. We could give it a training data set that has a few positive examples, and then use this data set to acquire a success classifier, or basically a binary reward function that's 1 when it's behind and 0 otherwise. And then once you kind of adapt your model using the training data set, you can then plan using your model to maximize reward. And this is what kind of the executed trajectory looks like after you plan with regard to the task of pushing the pencil case behind the notebook. Okay, so any questions on model-based RL for these multitask learning problems?
Sorry, can you just go over what you mean by like the form of the rewards?
Yeah, so what I mean by that is, do you basically have an equation that tells you like what R is as a function of S and A? And so in the case of like writing a digit or like trying to manipulate a ball to a certain location, the reward function may kind of be something that equals the negative like distance between the state and like the goal state for that ball. And if you have this equation, then you can just learn a model and plan with respect to this equation. If you don't have this equation, for example, if your states are images and your reward is like 1 if you were successful and 0 if you weren't successful, then you need to actually be able to optimize over actions, you need some equation that gives you the reward from the states. And if you don't have that equation, then you can basically train a neural network to tell you what the reward is given a state, an action, and your task identifier or your training data.
Okay, so it's just basically whether you have like an explicit like formulation of the reward versus having to like learn it. Okay, thank you.
Exactly, yeah. Asking, do we need to do reward shaping? This is a good question. So model-based reinforcement learning methods typically work better for shorter horizon problems, because if you have a very long horizon problem, and a sparse reward, then you need to roll out your model for a long period of time, and it may be difficult. Your model probably won't be accurate for that long of a horizon. If you instead have a long horizon problem with a very shaped reward, then model-based planning will be feasible. Or if you have a short horizon problem with a sparse reward, it will also be feasible. So this example on the slide right here is an example of a sparse reward where you just get 1 for success and 0 otherwise, but it's fairly short horizon because the robot only needs to kind of move its arm down and move the pencil case to the left. Yeah, and then is asking, can you explain again, what do you mean by the reward will change how you collect data? So the reason why this is basically here. So when you are optimizing over your action sequences to choose actions, you're going to be kind of optimizing for your action sequences with regard to your reward function. And then once you actually try to solve that task, you're going to be adding this data to your data set that's being used to train your model. And so if one task is to like move an object over here, and another task is to move an object over here, and you only train with regard to that first task, you're not going to see data of trying to move the object to the second position, and this will make it harder to actually perform that second task because the model won't be very accurate for those states. Is asking, the assumption here is that the meta learning model accuracy is 100%. It doesn't need to be exactly 100%. I think you're referring to this point right here, but it does need to be fairly accurate. If it starts to make a lot of mistakes, then your model is going to kind of exploit those mistakes, just like how it exploits errors in the dynamics model. Is asking, is learning the reward function a supervised learning problem? So yes. So in this case, this is basically a multitask supervised learning problem because you assume you have some labels of the reward function and you want to be able to predict those labels. But it's a multitask problem in the sense that you probably are predicting the rewards for multiple different tasks. And here it's basically equivalent to a meta learning problem in the supervised case. And then asking, is the outcome of this equivalent to training a joint MDP across these tasks? I'm not sure exactly what you mean by training a joint MDP because the MDP is the task itself, but this is one approach for kind of solving a policy or solving for behaviors across all of these tasks. Great. So I think those are all the questions. Now that we've kind of gone over the basics of model-based reinforcement learning for multitask learning, let's talk about the scenario where we have image observations, because things get a bit harder in that case. So, for example, we can take this graphical model here that's similar to the one that Karol showed on Monday last week, where you can kind of directly observe the observations O, and you can't observe the underlying states. So as a concrete example, say you want your robot to be able to use the spatula to lift up this object and put it into the bowl. And the only thing that you have access to is the kind of this camera image. And the robot can't directly access, for example, the position of the bowl or the position of the object. Also, when you have images, you don't necessarily have a direct reward signal. You can train a classifier, but you don't know the formula for the reward function. So yeah, as I mentioned, you can learn an image classifier to get the reward function. Another thing that you could do is provide an image of the goal. So you could provide an image that looks like this and try to reach that image. So these are kind of the approaches or options that we can use for specifying the reward. There are a few different approaches for model-based RL when you have these kinds of image observations. One is to learn a model in some latent representation space. Another is to learn a model directly of the observations. And the third is to learn a model of some alternative quantities. And we'll go over each of these approaches for the remaining time of the lecture. So let's first talk about learning models in latent space. The kind of key idea here is that we're going to learn an embedding that kind of embeds our observations into some usually lower dimensional space, and then just treat that lower dimensional space as our state space. So for example, if this is kind of our original graphical model, we can basically just try to learn an encoder that maps us back from the observations back to our states. And then once you learn this embedding, you can just do the same sort of model-based RL in that latent space. So this sounds pretty simple. There are a couple of papers that do this, or there's a couple of papers that did this back like 4 or 5 years ago. They're actually still fairly representative of the kinds of latent space models that people use today. So we'll talk about these. I can also talk about extensions on these and more recent approaches if people are interested. And the algorithm looks something like this. So you run some policy to collect data. You then learn a latent embedding of your observation space that maps from O to S and a model in that latent space. Then you can use this model to optimize over a set of action sequences, just like before, and then execute your planned actions and append the visited observation action next observation tuples to your data set. Cool, so there are a couple questions that arise from this algorithm. This is basically the same as before, with this just additional step of embedding the observation space. The first question that comes up is, what is the reward function for optimizing for your actions? The reward function that we'll use, and that's most commonly used, is just to, given the goal state that you're given, just measure the negative distance between your embedded state, or your embedded observation, and your embedded goal observation. So this is a pretty simple approach. Again, like I mentioned, you could also use something like a classifier, or if you do have observations of the rewards, you could learn a model of your rewards on top of your learned observation space. So you could learn something like this. But in practice, often approaches use something like this because you often don't, getting reward functions is actually pretty tricky in practice. Yeah, so asking, in the spatial example, would we be learning a model that maps images to the spatial orientation and location? That would roughly be the goal, although we would also want it to model things like the object and the bowl, and not just the spatula. In practice, I guess we'll talk about how we go about learning this embedding space on the next slide. One critical assumption with this reward function is that this distance in this latent space is actually an accurate metric. This assumption is actually pretty tricky in practice, because even if this representation space is useful for modeling the dynamics, distances in that space may not actually be meaningful. This may be something like, yeah, this is something like the L2 metric. You could also use other metrics in this space as well. Okay, so now how do we go about actually optimizing for the latent embedding space? What this first paper did is they learned an embedding and a model jointly. So they basically took something that looks like a variational autoencoder, except over 2 time steps, and jointly learned how to reconstruct images. They basically jointly learned kind of G of O mapping to S. Also, they learned a decoder that maps from S back to the original space. And then they finally also learned something that maps from S and A to S prime. This is the gist of the model. It's a little bit more complicated than that because it's actually kind of building upon variational inference. But if you're interested in the details, you can take a look at the paper. And in this case, they were trying to reach different goal states. So as an example, they would give it a goal state that looks like this, where the arm is kind of reached out to the top right. And then here's an example of a trajectory that's trying to reach that state. And you can see both the trajectory of the arm on the left and also the kind of the prediction from the previous time step. So these are kind of reconstructed images of the state. Now, if we give it a different task, which is to kind of curl the arm upward, it can also figure out how to reach this. And then finally, there's a third example where the arm is kind of reaching downward. And it's given this goal state and is trying to plan to reach this state. And each of these were actually, or all of this was actually learned with only around 300 trials, which would correspond to about 25 minutes of robot time per task, which is quite efficient. And then another way to optimize for a latent embedding space is to try to incorporate a little bit more structure into the process. And so in this work, I was trying to optimize for a latent embedding space where the latent space corresponded to points in 2D. And as a result of kind of imposing this structure on the latent space, it led to kind of features that tracked the objects through time. And specifically what it looks like is it's an autoencoder where the goal is to reconstruct images. We want to impose this 2D structure onto the latent representation. So to do that, the last convolutional layer, on top of the last convolutional layer, there's this spatial softmax, which essentially exponentiates each of the activations and then normalizes over the activations within the spatial dimensions. And so each of these different feature maps here correspond to different distributions over the spatial extent of the feature map. And then once you have this distribution over locations, essentially, you can then compute the expected location of each of those distributions to give you essentially expected XY coordinates for each of these feature maps. So then as a result, this is kind of a 32-dimensional vector where you get 2 dimensions for each of these feature maps, one for the X and one for the Y coordinate. And then you get something that looks like this. So this is visualizing only 2 of the feature points, but one of the feature points tracks the finger of the robot, and another one of them tracks the object. I also mentioned that the embedding is smooth, so there's actually an additional loss on top of this reconstruction loss that encourages the feature points to kind of, that penalizes the acceleration of the feature points. So you can encourage it to, maybe these feature points are kind of indicated by XY. You could encourage maybe you have something like this. This is the velocity of the point, essentially, the difference between the point's position at t+1 and the point at t. And if you want to penalize the acceleration, you can do something like this, where you compare the velocity at this time step to the velocity at the previous time step. This gives you something like the acceleration, and you can penalize this by basically just putting an L2 loss on this to give you points that are encouraged to be smooth over time. Okay, so this was the approach for learning the feature space. And then this is what the learning process looks like. So the policy, in this case, the goal was to put the block somewhere over here. And the policy is initialized as something that knows how to move its arm to the right position, but not necessarily the block. And over time, it's able to figure out how to put the block in the correct position. I may have drawn the blue square in slightly the wrong position, but it's able to figure out how to put it in the goal position, which was indicated by a goal image. Here's the final policy that it learns. And then we can also do it for other tasks. So in this case, this is the spatula task that we were motivated, that I gave with the initial motivation, and you can use this task to learn how to lift the object into the bowl, given the goal image, and also in this case, given the target configuration of the arm. Lastly, you can also actually visualize the feature points. So each of these circles is the visualized feature point for the image, and the X's is the feature points, the kind of the encoded feature points of the goal image. And you get trajectories that look like this, where the final policy is trying to minimize the distance between the goal feature points and the encoded feature points. And these skills were learned actually individually in this case, and they were learned in about 11 minutes of robot time per task, with the caveat that each of the representations were actually learned per task and per environment. Okay, so any questions on kind of learning in latent space? Feel free to raise your hand. And looking at the questions in the chat, I think I answered most of them. For the most recent one, this does require that you have a goal image from the same orientation as your observations. Otherwise, it may not work very well. Okay, so now one thought exercise, feel free to answer in chat or by raising your hand, is both of these two approaches, we're learning the embedding space by, like, with an autoencoder, by reconstructing the image. And why not just learn the embedding, like why not just learn G of O to S by simply trying to minimize the model error of the model in that latent space. So say we're just trying to minimize this with regard to the parameters of G, and where you basically just like set S to be the output of G. So what would happen in this case if you just tried to minimize, if you tried to optimize this embedding with regard to the model error in your latent space? So if it said a long time before convergence, bad embedding would result in a bad model, and the model would be largely dependent on the embedding. Suggested that maybe there's a trivial solution when the embedding is just constant, and it's also suggested that. So that's right. So there's actually a trivial solution to this, which is that if you optimize it only with respect to the model error, then your encoding can just always output 0 deterministically, for example, and then your model just has to always predict 0. And this wouldn't lead to a very useful embedding space, right? So this is why it's important to have some sort of objective to prevent this degenerate solution. So you need to do something. It doesn't need to be reconstruction, but you need to do something that prevents the embedding from collapsing. Okay, so to summarize, if you learn in latent space, you found that you can learn complex skills, visual skills from images very efficiently. It also, things like structured representations also enable this effective learning. The downside is that reconstruction objectives may not recover the right representation. So they're of course better than not having the reconstruction objective. But for example, in the work that I showed with the spatula, one of the tasks that I also wanted the robot to be able to do was to place a ping pong ball in the correct position. So the ping pong ball, this is kind of a low dimensional image of the robot with the ping pong ball here. And if you trained an autoencoder on this data, what you got for the reconstruction was something that looks like this. So it essentially learned to erase the ping pong ball because it was a very small object that didn't actually lead to a high reconstruction error if it didn't reconstruct it. And of course, the ping pong ball is, like, in this case, exactly what you wanted to know for the task. And this is an example of where a reconstruction objective may not recover the right representation. It may not actually focus on things that are relevant for the task. And so this kind of suggests that we need potentially better unsupervised representation learning methods. There has been a lot of development on this in kind of the last few years. There's still kind of more work to be seen on whether these new methods are effective for learning representations for these kinds of tasks. Do you have a question?
Yeah. Would you be able to give some examples of latent space? Like I guess something in latent space is not just a picture.
Yeah. So you could also, instead of having an image, you could also have other sensors. So maybe there's like in robotics, you could have audio, you could have tactile sensors, for example, and you may want to learn kind of a latent representation of those sensor readings. Beyond robotics, in autonomous driving, you may have things like LiDAR readings, for example. If you're in a setting like language models work pretty well, so you could probably just model directly in the space of language. Yeah, those are a few examples.
Thanks.
Great, and then just asking, what happens if you don't learn a latent space and just feed the observations into the dynamics model directly? And this is actually exactly what we'll talk about next. So we could actually skip the aside. We'll maybe get back to it later. But what happens if we just model directly in observation space? And this is actually something that we can absolutely do. So we can just kind of take the MPC algorithm that we did before, replace all of the S's with O's. That's exactly what I did here. And train the model to operate directly on your raw observations. So what this might look like in the context of robotics is you collect some data. So you can collect data that looks something like this. In this case, this is actually just a random policy for the most part. Then you can train your model to minimize prediction error. This actually corresponds to training a video prediction model. And you can get predictions that look something like this. That's predicting what the future will look like based on the actions the robot takes, or basically what its future sensor readings will show based on the actions it takes. You can also apply this to the towel data that I showed before to get predictions that look like this. One of the things that's nice about operating directly on observations is that it means that you don't have to prescribe a certain representation of your state. And for example, with deformable objects, it's actually quite hard to think about how you would represent a towel, for example. And if you essentially just operate directly on your raw sensor observations, then you can train models like this. And then once you have this model, you can then use that model to optimize for your action sequence with respect to some reward function. Again, your reward function could be a classifier or it could be some other metric that operates on your predicted images. There's a couple details here. So how do you predict video? This corresponds to a video prediction model, like I said before. There's a number of different models out there. Some of the important elements of this is to have a deep recurrent model that predicts multiple frames into the future. And it's also important for it to be conditioned on the actions that you take so that it predicts the future based on the planned actions that you want to take. And often these models are also stochastic. This is because there's often a lot of uncertainty about what the future will look like, and you want your model to be able to capture that uncertainty rather than simply blurring out, rather than simply kind of blurring the things that it's not certain about. If you want an example of what kind of the latest and greatest models look like, this is a paper from late last year from Ruben Villegas. The left is showing the predictions from the model, and the right is showing the ground truth on each of these pairs. And you see that it can actually predict pretty well what these, like how the robot will move and how the objects will move in response to the robot grasping the shorts or grasping the towel and moving it to a desired location. Okay, so that's how you predict video. How do you plan? You basically plan in the same exact way as before. For example, you could use a gradient-free optimization where you sample a large number of action sequences, including these two action sequences, predict the future for each action sequence, like as the predictions showed here, and then pick the future that is the most successful according to your reward function and execute the corresponding action. And then you can also repeat, if you want to replan, you can also kind of repeat these steps at each time step or every couple of time steps. Okay, so it's essentially kind of MPC, but in the visual space or in the kind of raw sensor space of these robots. So how it works is you might specify a goal. Like I mentioned before, there's a number of different ways to specify the goal. In some of our recent work, one way that we specified the goal is specifying where we want pixels to move in the image. For example, specifying that we want this red pixel to move up to where this green pixel is, and that we don't want this pixel here to move. Then we can run kind of visual MPC with regard to this goal. So we get a prediction like this that we think will accomplish the goal, and then we can execute those actions on the robot. This is with a model that isn't quite as precise as the latest models that I mentioned before, but it can still approximately accomplish the task. And of course, one of the nice things about these methods is that with just a single video prediction model, you can accomplish not just one task, but many different tasks, assuming that kind of the dynamics in the visual space and of the world are constant across these different tasks. So things like picking up an object, moving a sleeve towards the edge of the shirt, picking up an apple and putting it on the plate. You basically just need to kind of pass in the task you want it to do and some specification on images that allows it to optimize with regard to that task. And then it can plan to accomplish the task using its video prediction model. So here are a few more examples. Okay, so the benefits of modeling directly in image space is that this sort of approach can scale to real images. It also involves fairly limited human involvement. So once you start just collecting data, training the model is actually fully self-supervised. This was also true for the latent space methods as well. And actually, unlike the latent space methods, for the most part, we were able to accomplish a wider variety of tasks with a single model. Some of the downsides is that these images still do have limited background variability, and if you have a lot of variability in the background and the objects, then these models can have trouble capturing all of that diversity. And the skills here are still relatively simple. That's kind of a shortcoming, can be a shortcoming of a number of different things, including the capacity of the model to model complex interactions, and the ability to specify those tasks, and the power of the planner to be able to optimize for the right action sequence to accomplish those tasks. And these methods are also quite compute intensive because you have to actually plan using a video prediction model, which is quite large. Okay, any questions on modeling directly in your observation space? Okay, so the last set of approaches that you can consider is predicting something other than some latent representation or the image, predicting kind of alternative quantities. And what this looks like is, in different scenarios, you could ask, if I take a certain sequence of actions, will I successfully grasp an object, or will I collide with an object, or if I take a sequence of actions, what will my health or my damage be, for example? And what this is doing is you basically consider different possible things that the agent could do, and then you predict the answer to this question. You predict, kind of as a result of my actions, what is the outcome in terms of these specific metrics. This actually has a pretty close connection to Q-learning. So if you actually set the reward to be the probability of the event happening, then this actually corresponds very closely to Q-learning. And this can be used for things like grasping and avoiding collisions and so forth. And it allows you to only predict the quantities that are relevant to the task. The downside, of course, is that you need to manually pick these quantities, and you must be able to directly observe them. In grasping, you can kind of observe when you've grasped something by like looking at your fingers and seeing if your fingers are closed or not. If your fingers aren't all the way closed, that suggests that you're probably grasping something. and so forth. But in a variety of situations, like for example, the spatula task, you can't directly observe whether or not the object is, like you can't directly observe like a binary indicator for whether or not the object is in the hole. Once you learn a model like this, it's actually quite simple to actually perform the task. So for grasping, for example, if you have something that tells you, given a sequence of actions, whether or not you'll successfully grasp, then you can then optimize over a set of actions that lead to successful grasping. Okay, so those are kind of the three core approaches for model-based reinforcement learning when you have high-dimensional observations. So to kind of wrap up, I'll talk a bit about some of the takeaways between model-based methods and model-free methods. So today we talked a lot about models. Monday last week we talked a lot about model-free methods. What are kind of the trade-offs when considering these kinds of methods? So the benefit of model-based methods is that it's easy to collect data in a very scalable way because you can train a model with data that doesn't even have rewards labeled. It's also easy to transfer models across reward functions, and they typically require a smaller quantity of data that's supervised with the reward in practice. The downside is that models don't optimize directly for task performance, and so there's a bit of a mismatch between the objective, and sometimes the models may miss quantities that are important for the task. And sometimes the model is harder to learn than the policy. So for example, training a video prediction model may be more difficult than just predicting what the correct action is. And then lastly, you often need some assumptions in order to learn more complex skills because you need to be able to learn a model that is kind of suitable for those more challenging interactions. For example, if you have a lot of kind of harsh contact dynamics, then learning a model that can accurately predict the contact dynamics can be challenging. For model-free methods, the upside is that they make very little assumptions beyond having access to a reward function, although having access to a reward function can be a substantial assumption in some applications. They're very effective for learning very complex policies or learning very complex tasks because they just have to learn a policy. They don't have to learn how the world works. The downside is that they tend to require a lot of data. They're slower to learn, and it can involve a harder optimization problem in the multitask setting because you aren't just training for a single model of how things work. You're trying to optimize for many different queue functions or basically the queue function for many different tasks or the policy for many different tasks. And ultimately, it's likely that we probably want elements both of model-based learning and of model-free learning. They kind of both have benefits in different scenarios. Okay, so that's it for today. We kind of went over the basics of model-based reinforcement learning, including how to implement these kinds of algorithms, how model-based RL can be used for multitask problems, and challenges and strategies for handling high-dimensional state spaces with model-based RL. Next time, we'll talk about meta-reinforcement learning. So far we've talked about different ways to solve multitask problems, and for the next 3 lectures, we'll focus on solving meta-reinforcement learning problems where you care about being able to quickly learn a new task rather than just learning a set of training tasks.
Hi, I was wondering if you could go back to the part where you talked about learning a mapping from the image to like a physically meaningful latent representation.
Yeah.
I think you're one on the right, I think. I guess I was a bit confused about the whole like spatial softmax stuff going on and how you ended up with this. I thought it was really cool that you ended up with like the latent representation that like actually corresponded to points, but I wanted to understand a bit better how that worked.
Yeah, so the way that it works is we kind of assume that, well, I guess first we basically have this operation inside the neural network, but I'll first kind of emphasize that this autoencoder is trained end to end with regard to the reconstruction objective. So it's basically optimizing for a set of 2D points such that it can reconstruct the image effectively. Okay. Now, the special part about this autoencoder is this operation where we're essentially converting these feature maps to these 2D points. And the way that we're constraining this is we basically take a softmax over the extent of each of the feature maps. This gives us a distribution over each of the feature maps. And then we can take the expectation, which is written by this equation right here. We'll take the expectation over kind of the x extent, which is shown here, which is basically computing the average. So Sij is basically the probability distribution. S is the probability value for pixel ij, and this is computing the average over I and the average over j. And the result of this is basically kind of the expected value of that kind of distribution over coordinates, which will give you a kind of a 2D coordinate in this space. And both of these operations, the softmax and this expectation, are differentiable operations, which allow us to be able to backpropagate the reconstruction objective into the earlier layers of the network.
Okay. So like each of the 16 distributions could be like its own object. It's like a probability distribution over where that object is.
Yeah, so it can basically correspond to probability distributions over the location of different objects. We give it 16 so that it can kind of choose how it wants to use that itself. And based on how it's initialized, it may be easier for some distributions to represent some objects than others. You may not have 16 objects in practice, of course. So here we only have like 2 primary objects of interest. Yeah, and this is kind of what comes out of this kind of architecture.
Okay, and you get the full autoencoder, like you train this on its own before using it in any decision making. It's just the autoencoder training.
Yeah, exactly.
Okay, thank you. That helped a lot.
Great.
Yes, so I have a question in directly modeling observation space. So I'm wondering, so how can you define the objective using only the observations?
Yeah, so the model learning part is just kind of a generative model. I assume that you mean the objective for the planning process?
Yes, the planning process.
Yeah, so there's a few different ways to do this. I think I probably don't have a backup slide on it. Yeah, so there's a few different ways that you can do it. One is to train a classifier. Actually, the classifier is what was done in this earlier example. I didn't actually tell you that it was using images, but this example right here was actually training using a binary classifier, and we evaluated that binary classifier on the predicted images. And that's kind of one pretty effective way for doing this. In these cases, we're actually doing it a little bit differently. So we're telling it to move a pixel to a certain position, and then you need to actually evaluate for a video prediction where the pixels moved. And the way that we did it in this case is we actually used a video prediction model that isn't trying to directly output pixel values, but is actually outputting how pixels will move. And it's doing that in a differentiable way. And this allows us to kind of implicitly use the model's predictions about how pixels move in the objective itself, actually. So the way that it works is kind of, I didn't really want to go into these full details in the lecture, but the way that it works is it predicts these kernels that predict how images will move. These kernels are applied to the image to predict a transformed image. And then these different transformed images are composed to produce the image itself. And then this whole architecture is trained end to end with regard to the reconstruction error of this frame. And then when we're planning for that pixel, for moving pixels, we actually look at the kernels itself and how it predicts that pixels will move in the future. And we use that to evaluate the reward.
Yes, so from my understanding so this kind of definition of goal still some kind of uses the latent space. For example, when you train a classifier, and I can view the last layer before the output as some kind of latent space.
So you can view it like that. It isn't that the last layer isn't being used in any way of the classifier. So we're only using kind of the output of the classifier when we're planning. We're just using kind of whether it predicts that this was a success or whether it predicts that it was a failure. And then the planning is done in the image space, and the predicted images are passed into the classifier.
Yeah, so for example, when you optimize the model in the observation space, when you use the images directly, so for example, if you are still using L2 loss, so I kind of think that this kind of loss may not characterize the situation very well.
Yeah. So,
for example.
Yeah. So for the model training, a lot of the models that I showed were actually deterministic and optimized with regard to an L2 loss. But a lot of the kind of more recent models that are very accurate don't use L2 loss directly. So this model, for example, uses latent variables, like a VAE style model, to capture its uncertainty in what will happen in the future. These latent variables aren't equivalent to a latent space. They aren't capturing kind of exactly what the state is, but they are able to capture the kind of the uncertainty about the future. So you can use like a VAE style loss, which is kind of L2 reconstruction or something like L2 reconstruction plus a KL term. There are also models that use GAN style losses to optimize the model predictions. And there are also methods that kind of optimize likelihood, for example.
Yeah, thank you so much.
Great. And then asking at the chat, explaining why hindsight experience replay works well. So let's go back to the beginning here. And actually, I like using this example. So one of the reasons why it works well, or kind of the intuition, is that if you have a lot of different tasks that you want to accomplish, a lot of different goals that you want to figure out how to reach, a standard approach would just keep the data completely separate for those different goals and basically practice this task of passing a lot, practice this task of shooting a lot, and so forth, and keep the data completely separate. However, when you attempt one task, you often end up kind of reaching a different task or reaching a different goal on accident. And you can use those accidental successes to actually help train the other tasks. And by using those, you can actually kind of share data across tasks. And when you're trying to reach a large number of different goals, this process allows you to be significantly more efficient, basically by sharing data across all of your tasks, than if you were to try to attempt the task individually. Another reason for why it works is that if one task is easier than another task, they can actually help provide a little bit of a curriculum, because practicing that task will give you some reward signal for the correct solution, and that will allow you to getting some kind of signal for that will actually allow you to explore in different ways, because you'll know how to solve that, and then when you solve that task, you'll accidentally solve other tasks, and so forth. So kind of the intuition is that it allows you to share data across different goals, and it gives you kind of signal for it gives you kind of reward signal for things that you accomplished on accident when trying to solve a different task. Oh, looks like there's one more question. So while choosing tasks, would this also mean that the entropy of the task goals for the tasks we choose should be high to maximize this? Right, so when you're kind of going about collecting data, you need to choose some distribution over goals that you want to pass your policy to try to accomplish. There are some approaches that basically try to kind of reach a much wider range of goals in order to help explore, rather than just reaching a very narrow set of goals. And this sort of kind of maximum entropy over goals can be an effective technique for trying to explore. So one example paper that you could look at that does something like that is called SkewFit, and it's by Vici Pong et al. Okay, great. I'll see everyone.